Hydrogen gets the headlines. Electrolyzers get the funding announcements. Gigawatt projects get the political speeches. But inside every serious green hydrogen plant, behind the stacks, behind the piping, behind the glossy renderings, there is a quieter system doing the real work. It does not produce hydrogen. It does not split water. It does not appear in most press releases, but without it, nothing runs. That system is power electronics. If you remove power electronics from a hydrogen plant, the electrolyzer does not turn on. If you destabilize it, efficiency collapses. If you underdesign it, stack lifetime falls. If it fails, the plant stops. The energy transition depends on this layer more than most people realize, and yet it remains largely invisible in mainstream hydrogen discussions. To understand why, we need to start from first principles. Electricity from renewable sources does not arrive in the form electrolyzers need. Wind turbines produce variable frequency AC power. Solar farms generate DC that must be inverted and synchronized to the grid. Grids operate in alternating current at fixed frequency and voltage, but electrolyzers require tightly controlled direct current. The transformation between these forms is not trivial. It is the domain of rectifiers, inverters, converters, filters, transformers, and control systems. In other words, power electronics. An electrolyzer is fundamentally a DC device. Whether alkaline, PM, or solid oxide, it requires stable, precisely regulated DC current. Current density determines hydrogen production rate. Voltage influences efficiency. Ripple and harmonics affect degradation. Temperature interacts with load variability. You cannot simply connect an electrolyzer stack to a wind turbine and expect it to operate optimally. Between the renewable asset and the stack sits a conversion system that conditions the power to within strict tolerances. This is where the hidden economics begin. Every inefficiency in the power conversion chain increases the levelized cost of hydrogen. If your rectifier loses 2% more energy than expected, that loss compounds across megawatts operating thousands of hours per year. If harmonic distortion stresses transformer insulation, you face unplanned downtime. If switching losses are high because outdated semiconductor modules are used, operational expenditure increases. These are not academic details, they are cost drivers that directly influence whether a plant achieves $2 per kilogram or misses the threshold. The conversation around hydrogen often focuses on electrolyzer capital cost per kilowatt. But the stack is only part of the electrical architecture. There is medium voltage infrastructure, there are step-down transformers, there are rectifier cabinets converting AC to DC, there are filters managing harmonics, there are control systems ensuring current ramp rates stay within safe boundaries. In large installations, the power electronics footprint can rival or exceed the visible electrolyzer footprint in complexity. This becomes even more important in a world of rising grid stress. Global electricity demand is increasing, driven by electrification and data center growth. Variable renewable penetration is climbing. Grid-forming capabilities are becoming critical. The hydrogen plant is not an isolated system. It is an industrial load embedded in a stressed network. If its power electronics are poorly designed, it can amplify grid instability rather than absorb excess renewable power. Here is where the system's collision appears. Hydrogen is often framed as a solution to renewable intermittency. Excess wind or solar can be converted into hydrogen when supply exceeds demand. But this flexibility depends entirely on power electronics that can handle dynamic ramping. Electrolyzers must follow load changes without damaging membranes or catalysts. That requires converters capable of fast response and precise control. Without that layer, the flexibility narrative collapses. Now consider semiconductor materials. Traditional power electronics relied heavily on silicon IGBTs. But as switching frequencies increase and efficiency requirements tighten, silicon carbide and gallium nitride devices are gaining traction. These materials allow higher switching speeds, lower losses, and more compact designs. In high-capacity hydrogen plants, that translates into smaller cooling systems, reduced footprint, and improved efficiency. The difference between conventional silicon and silicon carbide is not marginal at scale. It affects megawatt-level losses. This is not merely engineering elegance, it is competitive edge. Under system stress, the plants that survive are those with superior utilization, lower operating losses, and predictable performance. If subsidies decline and power prices fluctuate, only the most efficient configurations remain bankable. Power electronics design becomes a survival factor. It influences transformer sizing, cooling requirements, and even the plant's ability to participate in ancillary services markets. Ancillary services are another under-discussed dimension. Some hydrogen plants aim to monetize grid support functions, such as frequency regulation. That is only possible if their power conversion systems are responsive and compliant with grid codes. Grid-forming inverters, harmonic filtering, and reactive power control are not optional features. They determine whether a plant is an asset or a liability to the network. Zoom out further. The energy transition is electrification at scale. Electric vehicles, heat pumps, industrial furnaces, electrolysis, data centers all depend on conversion layers. Solar panels produce DC, but the world's grid runs on AC. Batteries store DC, but supply AC. Hydrogen production consumes DC derived from AC. Every interface requires conversion. That conversion is governed by power electronics. This means the energy transition is as much about semiconductors and switching frequencies as it is about molecules. Yet, policy narratives emphasize hydrogen targets and renewable capacity without equal emphasis on converter manufacturing capacity or silicon carbide supply chains. If power electronics supply tightens, hydrogen deployment slows regardless of electrolyzer ambition. There's also the issue of power quality. Electrolyzers are sensitive to voltage fluctuations and current ripple. Excess ripple can accelerate degradation in PEM stacks. That shortens lifetime and increases replacement cost. A poorly filtered rectifier may save capital up front but create long-term operational risk. Developers evaluating equipment bids often focus on stack efficiency, but overlook conversion quality metrics. In stressed capital markets, this short-term optimization can backfire. Let's examine cost structure. The levelized cost of hydrogen is influenced by capital expenditure, electricity cost, efficiency, utilization, and maintenance. Power electronics influence all five. They contribute to CapEx directly. They affect efficiency through conversion losses. They influence utilization by enabling flexible ramping. They impact maintenance through thermal management and component lifespan. Even financing costs can be affected if lenders perceive electrical integration risk. This is where the competitive edge test applies. If subsidies decline and utilization misses optimistic projections, who survives? Plants with efficient conversion, resilient control systems, and robust integration are better positioned. Those with marginally cheaper stacks but weak power electronics may face higher downtime and lower net output. Now consider regional context. In markets with unstable grids or high renewable penetration, conversion complexity increases. In regions with strong, stable grids, integration may be simpler. That geographic variation means power electronics design must adapt to spatial conditions. The future hydrogen map will not be defined solely by resource availability, but also by electrical infrastructure compatibility. The hidden layer becomes even more relevant in hybrid systems. Many industrial hubs are exploring integrated configurations, combining solar, wind, batteries, and electrolysis. Coordinating these assets requires advanced converters and control software. The hydrogen plant becomes part of a microgrid-like environment. Power electronics become the orchestrator. This orchestration is not trivial. Switching frequencies create heat. Heat must be managed. Thermal management systems add complexity. Cooling influences reliability. Reliability influences bankability. The chain is continuous. In discussions about green hydrogen scaling, manufacturing of electrolyzer stacks receives attention. But converter manufacturing capacity rarely enters the conversation. If gigawatt-scale deployment accelerates, demand for high-power rectifiers and advanced semiconductor modules will rise sharply. Supply chain constraints could emerge not at the membrane level, but at the silicon carbide wafer level. That reality reframes the narrative. The energy transition is layered. Molecules matter, but electrons must be controlled first. Hydrogen cannot escape the laws of power conversion. At this point, it becomes clear that any serious evaluation of green hydrogen economics must include the electrical architecture. A plant is not just an electrolyzer array connected to renewables. It is a system of transformers, converters, filters, control algorithms, cooling loops, and protection schemes. Ignoring this layer leads to underestimation of complexity, and complexity affects timeline. Delays in grid interconnection studies often revolve around harmonic analysis and fault current calculations. Grid operators assess whether new large loads will distort voltage waveforms or create instability. The design quality of power electronics directly influences approval timelines. Now, let's address survivability under stress. If electricity prices fluctuate wildly, flexible operation becomes essential. Power electronics that can handle rapid ramping without excessive degradation enable operators to run when power is cheap and idle when expensive. That arbitrage capability improves economics. Without responsive converters, flexibility claims are theoretical. This is also where artificial intelligence intersects. AI workloads increase power demand volatility. Data centers operate with large, nonlinear loads. As grids integrate more such loads, power quality challenges increase. Hydrogen plants embedded in these systems must maintain stability. Advanced converters with sophisticated control algorithms become critical. In this sense, the future of hydrogen is tied to the future of semiconductor technology. As switching devices improve, efficiency improves. As efficiency improves, hydrogen cost falls. But if semiconductor supply chains become constrained or geopolitically fragmented, deployment could slow. We often frame hydrogen as competing with batteries, but both rely heavily on power electronics. In fact, batteries are even more converter dependent. This suggests the real competition is not molecule versus electron. It is conversion capability versus system complexity. The silent technology does not generate headlines because it lacks narrative simplicity. It is technical, embedded, and unglamorous. Yet it determines whether ambitious hydrogen targets translate into operational reality. For developers, consultants, and investors navigating this landscape, the lesson is straightforward. Do not evaluate hydrogen projects at the stack level alone. Examine the power conversion architecture. Ask about harmonic mitigation, semiconductor choice, thermal margins, ramp rates, and grid compliance. These factors influence lifetime economics more than many promotional materials admit. If you are building or evaluating projects in industrial hubs, this systems-level awareness becomes essential. Hydrogen does not exist in isolation. It sits within an electrical ecosystem, and that ecosystem is governed by conversion physics. For professionals who want to understand these deeper layers, from cost drivers to integration challenges, H2 Hub by Renee Energy provides structured insights into how hydrogen projects survive under real-world system stress. The focus is not on hype, but on execution, economics, and infrastructure realities. As we move deeper into the decade, the clean energy conversation will mature. Headlines will shift from capacity announcements to operational performance. When that shift happens, the silent layers, power electronics, control systems, and integration architecture will determine winners and losers. Hydrogen may carry the molecule narrative, but the energy transition runs on electrons disciplined by semiconductors. If we fail to recognize that, we risk misdiagnosing both opportunity and constraint. The next time a gigawatt hydrogen project is announced, look beyond the electrolyzer brand. Ask what lies behind the cabinets, inside the converters, within the switching modules. Because that is where the real transition is happening. Quietly, continuously, and critically. And if that layer fails, everything else fails with it.